So when I introduced the concept of power factor in class on Tuesday, I gave you guys two definitions effectively that were related to each other. So our power factor was defined to be the ratio of the average power to the apparent power, and that also happens to be the cosine of our power factor, right? I talked about how average power is effectively the part that we as consumers pay for, and apparent power is the part that our industrial utilities pay to generate. And that the utility companies want that ratio to be as close to 1 as possible so that they're not losing too much money generating power that winds up getting sent right back to them, okay? So in some industrial applications, particularly in manufacturing and all of that kind of good stuff, it's very common that the power factor at which that manufacturing plant operates is less than something that the electric utility wants. And so to encourage the manufacturing plant to do better, they typically fine the manufacturing plant every month while their power factor is below some particular threshold. That's going to vary from electric utility to electric utility. Sometimes it's 95%, sometimes it's 97.5%, sometimes it's 98%, but they usually want your power factor to be particularly high. They don't really care whether or not it's leading or lagging as long as it is above some particular threshold. They won't wind up finding you, okay? So the concept of power factor correction is what industry does to raise their power factor closer to unity in order to avoid facing those monthly fines, okay? So we are going to take a look at this by looking at an inductive load or looking at the power triangle of an inductive load and trying to see what could be done to increase the power factor, right? So this is my complex plane, real axis on the horizontal axis, imaginary on the vertical. And this vector here, which I'm going to call S old, represents the complex power absorbed by a particular load prior to power factor correction. Okay, so let me just make a note over here. The projection of S old onto the real axis is our average power, P old. The projection of S old onto the imaginary axis is our reactive power prior to power factor correction, which we're going to call Q old. And the angle formed between the real axis or the positive real axis and our complex power is going to be our angle, theta old. So if I want to increase the power factor at which this load operates, meaning make it closer to 1, do I need to make that angle, theta old, larger or smaller? Smaller, absolutely right. So I need to make that angle smaller, and there are a couple of different ways that we could accomplish this. We're going to look at both of them. I want to tell you from the jump that one of them is completely and utterly asinine in practice, okay? So while mathematically it works out perfectly fine to lower that angle, in practice it is just a terrible idea. We'll talk about what that is. And that's the one that we're going to do first, okay? So let me use a slightly different color here. So let's say that I was able to make my load absorb more average power while keeping the reactive power the same. My new went a little too far there. Vector here, S new, would look something like this. And if we projected this down like so, we'd have some new average power, but our reactive power would remain exactly the same. And our angle here, theta nu, is smaller, which means that our power factor should be increased, at least from a mathematical perspective. Now, can anybody tell me why this is completely and utterly stupid to do in practice? You're increasing the amount of average power you draw. Why is that dumb? That's what we pay for. So you're running up your utility bill in order to avoid paying a fine. Doesn't make any practical sense to do that, right? Effectively, what you are doing here is increasing the resistance of your load, which is going to increase the amount of average power consumed, which once again is literally what we pay for as a consumer in order to avoid a fine for having our power factor too low. Does it make sense to run up your electricity bill in order to avoid paying a larger bill? No, completely and utterly asinine. So mathematically it works. In practice, it's about the dumbest damn thing you could possibly do. So let's erase this one because of how wildly stupid it is. So our other approach then is going to be, we need to figure out some way to keep the old constant so that our electric utility bill stays roughly the same while lowering the amount of reactive power that is drawn. So effectively, we're looking for a situation like this, where our P old is constant. We have some Q new, and now our theta nu is lower, resulting in an increased power factor. Okay, where let me make a note here. So here's S new, and S new is what's going on after power factor correction. So how is this going to be accomplished? Well, we need to add something into our system that will produce negative VARs, right? We're lowering the reactive portion while we're keeping the average portion the same. So we need something that's going to lower the amount of VARs that are consumed. So let's look at a couple of things here really quickly. I'm going to write down those alternative relationships that we developed at the end of our last class meeting. So we had S in general could be expressed as the magnitude of an RMS phasor voltage over Z conjugate, or it could be expressed as, that voltage should be squared, the magnitude of the current squared times Z. Might be using very slightly different notation than I did on Tuesday. I might have said that that was V effective and I effective. It's the same thing. It's just the magnitude of our RMS phasor voltage and current respectively. So let's look at what a resistor does in terms of its complex power. Okay. So for a resistor, actually, let me write this out explicitly. our impedance, ZR, is just R, right? So from this, we could say that SR is just going to be the magnitude of the voltage squared divided by the resistor value, or the magnitude of the current squared times the resistor value. Because the conjugate of a real number is just the real number. There's no imaginary part to change the sign on, right? So what does this, or these two expressions, tell us? So let me ask you guys what I hope is a pretty simple question. Do you see any J's anywhere up in here? No. So if there's no J component, then that means that this power is purely real, right? So resistors absorb average power. That's what they do in a system, okay? So if we wanted to increase the amount of average power that was drawn by our load for whatever reason, we would add resistance. Now let's look at an inductance. So we know that the impedance of an inductor is J omega L. So the complex power absorbed by an inductance is going to be the voltage magnitude squared divided by negative J omega L. And we know that 1 over J is the same as negative J in the numerator. So 1 over negative J should look like positive J in the numerator. So that's going to look like J times the magnitude of the voltage squared over omega L. In terms of our current, we are just going to have the magnitude of our current squared times omega L, and I'm just going to choose to put the J out in front there. Okay. So what do we see here? Well, there's no real part, there's only an imaginary part for the complex power here, right? So we have no real power whatsoever, so inductors are only contributing reactive power. Caleb, how may I help you?
So I'm kind of confused why we have a negative of J in the first part, because wouldn't that just be J omega L?
So look at our expression here. We want Z conjugate. Conjugate means we change the sign on the imaginary part. Yep. So we have imaginary power only. Can either of those terms literally ever be negative? Omega is always going to be a positive number. L is always going to be a positive number. And because we're dealing with the square of the voltage and the square of the current, that's also always going to be a positive number. So this tells us that inductors absorb reactive power. Just as a quick question to make sure that we're all on the same page here. If my load absorbed more reactive power, what would happen to Q? Would it get larger or smaller? Larger. So if I make my load more inductive, Q is going to actually increase. To some extent, yeah. That's not necessarily what we're trying to do, but it is a side effect of what we are doing. So by what I mean by that very explicitly, what we're trying to do is we're trying to get our power factor to be closer to 1. as a consequence of that, any leading power factor that like we have, so the current is leading, excuse me, any lagging power that we have, power factor that we have, where our current is lagging our voltage by some amount, the amount by which it lagged is going to get smaller the closer and closer we get to 1, because our angle is getting closer and closer to 0. So that is happening, but that's not 100% what we're doing. It's just a consequence of what we're doing. So just so that we're all on the same page here, effectively, I have some positive amount of reactive power Q old, and then I'm going to add some more positive reactive power if I introduce more inductance here. That's just going to make that number larger, or it's going to push this guy up whenever I introduce more inductance into the system. Okay. So hopefully we figured out by process of elimination that we're going to have to wind up introducing a capacitor to this guy, but let's see why that works explicitly. Okay. So for a capacitance, we know that our impedance, ZC, can be expressed as negative J over omega C. And from this, we're going to have our magnitude of our voltage, V, squared. And now I'm dividing by ZC conjugate, right? So when I divide by ZC, that means that I'm multiplying by the reciprocal of ZC. So that would look like omega C over negative J. When I conjugate this impedance, that's going to look like positive J. What's 1 over positive J? Negative J. So this is going to look like negative J times our voltage squared times omega C in terms of our voltage, and in terms of our current, it's going to look like negative J times the magnitude of the current squared divided by omega C, since it's just direct multiplication there. So our complex power is purely imaginary, but it's also always negative. Okay. So this means that capacitors supply reactive power, or they absorb negative reactive power. So that's what's going to provide the reduction in VARs that accomplishes power factor correction. We need to add capacitance to our system in order to accomplish that. Okay. So the difference between S old and S new, let me make sure I'm getting the sign correct here, is going to be S cap. I'm putting a star right here because I'm honestly can't remember off the top of my head whether or not I'm missing a negative sign, so I might need to come back and put one in, and we'll sort that out here in literally just a moment. Okay. So let's take that relationship and expand on it slightly. Okay. So if I said that S old were equal to P old plus JQ old, that's just my complex power before power factor correction expressed in rectangular form. And I said that S new were equal to P old plus JQ new. Then S old minus S new would come out as P old plus JQ old minus P old plus JQ new. What's the result of this going to be? So I'm going to have P old minus P old. So the real part completely cancels out. Then I'm going to have JQ old minus JQ new. Like so. And this is telling us effectively how much reactive power our capacitor needs to supply in order to make up that difference. So we can use this relationship and this relationship right here in order to actually solve for a particular value of capacitor that will correct our power factor to some specific thing. Okay. So just rearranging this equation right here, or actually what I'm doing is I'm setting these two equations equal to each other and then solving for C. What I will find is that my capacitor value C is going to be equal to negative QC divided by omega times V magnitude. Let me draw that better so we can make sure we can see this tilde over it. Squared. Where that VC thing right there is just telling us we're using the voltage drop that's across the capacitor, okay, explicitly. Now, there's nothing wrong with this expression right here, but it's kind of limited in its application because we have to actually go through the work of solving for the reactive power supplied by the capacitor and all of that kind of good stuff. It's not directly related to our our old power factor or our new power factor. Brock, how may I help you? There should not be a J there at all. There's a J on both sides of the equation, so that's going to cancel out. The reason that there's a negative sign there is because QC will always be a negative quantity inherently because it's the power absorbed by a capacitor, which literally we just proved right up here is always a negative quantity. So we can put this in terms of our old power factor and our new or target power factor, or at least something pretty close to that, as P old times the tangent of theta old minus the tangent of theta new divided by that same omega times VC magnitude squared. So 99 times out of 100, this is the expression that I would use because 99 times out of 100, we're just going to be given information about our old power factor, our new target power factor, our frequency of operation. So it's less other stuff we have to solve for. Yes, so this is telling us what size of capacitor to put in our system in order to achieve a specific amount of power factor correction. Absolutely right. So let's look at our in-class assignment problem number 1. Let me pull this up. This should be ICA number 5, if I'm remembering correctly. Yeah. Let's close that out. Okay, so I gave you guys a little bit of a word problem here. We're going to draw what I'm going to arguably call a circuit just so that we understand effectively what's going on. Okay. So on the left-hand side of this circuit, I'm going to have my voltage source. I'm told that this is a 120 volt RMS source. So I know that the magnitude of VS is 120 volts RMS. I do not know the phase angle. Turns out I'm not going to need to know it whatsoever anyway. At an operating frequency of 60 hertz. Giving myself a pair of terminals here. And then over here on the right-hand side, I have my load. So I'm told that my load absorbs 4 kilowatts at a power factor of 0.8 lagging. And let's see, we are told that our target power factor, effectively PF new, is 0.95 lagging. So I said a moment ago that we're going to introduce capacitance to our system. Okay, we're going to do that literally by just putting our capacitor in parallel with our load. Can anybody tell me why we might be putting our capacitor in parallel with our load as opposed to in series with our load? So we're putting it in parallel so that the voltage applied to our load is unchanged, right? So if I plug something into an outlet, if I put something in series, that's going to have a voltage drop over it, which means my load is going to be receiving a smaller voltage, which means my load might not work correctly, right? If I put my capacitor in parallel, the voltage drop applied across my load literally does not change at all. So everything's going to continue to work, right? So what we are going to see is that if we did an analysis of this thing, and we can go into greater detail here, effectively what's going to happen is that the magnitude of the current that's leaving our voltage source is going to be smaller. What that means is that we could use smaller conductors because they're not carrying as much current, which is going to be cheaper for our electric utility. We're also going to see that our power factor is reduced, which means, or excuse me, power factor is increased, which means we're not going to be paying any fines or anything like that as well. So there's multiple advantages to putting it directly in parallel. All right, so I'm going to write down our equation for determining capacitance. C is equal to P old times tangent theta old minus tangent theta new divided by omega times the voltage drop across our capacitor in magnitude squared. So I want you guys to tell me which pieces of information do we have? So do we have P old? 4 kilowatts, absolutely right. Do we have theta old? Kind of. We can very easily solve for it, right? So we have enough information to compute theta old very easily. How would we do that? So we're going to use that power factor of 0.8 lagging, but how are we going to use that? Inverse cosine or arc cosine, absolutely right. So arc cosine of 0.8 should be 36.87 degrees. Is that supposed to be positive or negative for the angle? Why? There we go. Yep, I want that Pavlovian response of when I say, why is that angle positive or negative? You say correctly leading or lagging. So you're doing a great job. All right. Do we have theta nu? We can find it the exact same way, right? So that's going to be the inverse cosine of 0.95. Which is 18.195 degrees. Do we have omega? So 60 hertz is our linear frequency f. How do we use f to get omega? Too much thought. Multiply by 2 pi. The 1 over t is equal to f. We could go that route, but we don't really need to, right? Anytime we have our linear frequency given in hertz, if we want our angular frequency in radians per second, we simply multiply by 2 pi. Okay? So 2 pi times 60, I'm going to call this 120 pi radians per second. Do we have the magnitude of the voltage drop across the capacitor? Use your words. What? 120 volts RMS, absolutely right. So we have all 5 of the pieces of information that we need to plug into that equation pretty darn easily here. So put all of that together and tell me what C is. So 4,000, I mean, the answer is above, obviously. So tangent of what I have is X minus tangent of what I have is Y. Nope, not a single one of them. So I got 310.438 microfarads. Looks like I got a little bit of rounding error, but not a big deal. So for that particular system, it takes a 310 microfarad capacitor in order to push our power factor up from 0.8 to 0.95 leading, or excuse me, lagging. So this isn't part of this problem, but what if we wanted to push our power factor up to 0.95 lagging? What would change? Or excuse me, 0.95 leading, thank you. Yep. So I'm just going to put C lagging here. Let's find what C leading would be. It's probably just rounding. Yeah. I stored stuff in my calculator, so instead of 36.87, I have like 36.868, yada, 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 and all that kind of stuff. So 1 microfarad isn't enough for me to think you did anything wrong. Yeah. 120 pi. So if we had a leading, or if we were looking for a leading power factor, effectively that theta nu calculation, we would just add a negative sign in front of the angle because we know that a negative angle gives us a leading power factor. So putting in negative 18.185 or excuse me, 195 degrees, I wound up getting a 794.805 microfarad capacitor. So about 2.5 times as large. So if you were the customer here, would you rather hit a power factor of 0.95 lagging or a power factor of 0.95 leading? Because to the utility, they're the same thing. You're within their tolerance, so they don't care. It's the same distance away from 1 because 0.95 lagging is, 0.05 away from 1. 0.95 leading is 0.05 away from 1. Somebody over here had their hand raised. Okay. So I would argue that you're probably going to want to go with the lagging power factor simply because the capacitor is smaller and therefore probably cheaper. They both have to be rated for the exact same voltage, all of that kind of good stuff. But typically speaking, a larger capacitor is physically larger, which means it requires more materials and should be slightly more expensive. So realistically, this is a case where doing the minimum is probably better than putting a ton of extra effort into it. Yes. So for this system right here, our load is absorbing 4 kilowatts and we're dealing with 120 volts RMS source. So the physical size of the capacitor that could accomplish this would be a small thing because it doesn't have to be rated for a huge voltage or anything like that. That being said, on an industrial scale, where our load might be drawing megawatts of power and all of that kind of stuff, even though the nominal value of the capacitor might be, 300 microfarads or something like that, its physical size is going to be that cabinet or something like that. They're going to be big, beefy things. So
it can be, like I could have like 300 microfarad capacitor. This being the loss.
Yeah, and it just depends on what voltage it's rated for because it needs to be able to withstand dielectric, withstand and all that kind of stuff, yeah. But- All right, so that's the first problem, fairly straightforward, I think. Now let's look at this second problem. So here we have a similar situation. In this case, the magnitude of my voltage is 230 volts RMS at 50 hertz. So based on these numbers, we're somewhere in Europe. And we are connecting to our voltage source a motor that has an equivalent impedance of Z motor is 25 plus J10. We're going to perform power factor correction. Sorry, that's not what I meant to do there. And we want to figure out what value of C gets us to a power factor nu of 1. So I'm going to write down my equation again. C is equal to P old times tangent of theta old minus tangent of theta nu divided by omega times the voltage drop across the capacitance magnitude squared. So do we have P old? No, we do not, but I would argue that we have enough information to find it, okay? So how would I find the complex power absorbed by my motor prior to power factor correction? So what two pieces of information do we have about the motor? We have its impedance, and we know the magnitude of the voltage drop across it. Is that enough information? Absolutely. We have an equation that literally allows us to use those exact two pieces of information to find our complex power, right? So that's going to be the magnitude of the voltage drop across the motor squared divided by the conjugate of the motor's impedance, right? Wrote that one down earlier today, came up with it and applied it on Tuesday. So nothing particularly wild or crazy here. So we're going to have 230 volts RMS quantity squared over 25 minus J10 ohms. Caleb, why is it a minus J10 there? There we go. Throwing that into my calculator, I get 230 squared divided by 25 minus 10 pi. So in rectangular form, I get 1,824.138 plus J 729.655 volt amperes. And in polar form, I got 1,964.657 with an angle of 21.801 degrees volt amperes. So what's PL? Which part of complex power is average power? Is it the real part? Is it the imaginary part? Or is it the magnitude? It's the real part. So which of those is the real part? 1824.138. I am doing it that way. Yeah, I mean, realistically, I'm gonna just store crap in my calculator and all of that kind of stuff and use the bits and pieces that I need. But I, I literally, I never calculate for average power, reactive power, or anything like that directly. I always just calculate for complex power and then just take the part that I need. I don't necessarily always write all of that down, but okay. So we figured out what P old is. What's theta old? The 21.801 degrees voltamperes. Or, sorry, I don't need the voltamperes. 21.801. Absolutely correct. What's theta nu? So it's going to be the inverse cosine of the 1 power factor. What's the inverse cosine of 1? 0, absolutely. What's omega going to be? (100 pi). So 50 hertz times 2 pi is 100 pi radians per second. And what's the magnitude of the voltage drop across our capacitor? 230 volts RMS, absolutely right. We now have all of the parts that go into our equation, so we plug it in. So the magnitude of what I have stored is x times the tangent of the angle of what I have stored as x minus the tangent of 0 divided by 100 pi times 230 squared. 47.287 micro farads. I'm off by about 4 microfarads, so I'd be willing to bet I just fat fingered a number in my calculator wrong or something like that. The process is correct. I might have just made a small mistake, or I might have made a mistake when I solved it the last time. But anyway, I'm not too worried about it because I know that the process is right. Okay. So we've worked 2 example problems that are I would say the first one was of an easy difficulty, and the second one was of a medium to easy difficulty. So now I want to work problem 2 from the homework set on power factor correction, because I would argue that it's one that's closer to hard. Okay. So I'll write down the details here. So this is homework number 5, problem 2. And we are told that we have a composite load consisting of 2 loads connected in parallel. So I'm going to represent that over here by something like this. So this is my first load. I'm going to put number 1 up here. Here's my second load. I'm going to put number 2 over here. Okay, so that's my composite load. in total, they could draw 2.6 kilowatts. So I'm going to say that P composite is 2.6 kilowatts at a power factor of 0.82 lagging. So PF composite is 0.82 lagging. The first load draws 1.4 kilowatts at a power factor of 0.75 lagging. The loads are supplied with a voltage of 120 volts RMS. At a frequency of 60 hertz. And we are asked to determine the complex power absorbed by the composite loads, the complex power absorbed by load number 1, the complex power absorbed by load number 2, and the capacitor value needed if we want to increase the power factor for the composite load to 0.98. All right. So I'm going to go ahead and put the capacitor in here to remind us that we are going to be doing power factor correction here in a moment. So the first 3 parts are just reinforcing the relationships that we learned in our last class. Okay? So if I want to find the complex power absorbed by my composite load, how would I go about doing that based on the information that I was provided? Just to be clear, I was given the average power and the power factor. Do we have an impedance given in this entire problem? We do not. For what it's worth, we literally answered a problem with this same information on Tuesday. Average power and power factor. So I'm going to give you guys a very strong hint. By definition, power factor is the ratio of the average power to the apparent power, and it is also equal to the cosine of the power factor angle. Complex power can be written as apparent power with an angle of the power factor angle. So how can I solve for apparent power? Right, so the power of our composite load divided by the power factor of our composite load. How would I find the angle? All right, and now I can just get rid of those bars, and I'll be damned, we have an equation to give us the whole thing. Right? So that's going to be 2.6 kilowatts divided by 0.82 with an angle of the inverse cosine 0.8. 110 kilo. That can't be. Mm-hmm. Mm-hmm. I want to look at your calculator in a moment because I think you're in a weird mode or something. Because these should both be ABA. So I got 2.6 plus J 1.815 kilovolt amperes in rectangular form and 3.171 angle 34.915 kilovolt amperes in polar. Brock, I think you said something to the tune of 3,170 something. Yeah, which would be in volt amperes. So, okay, so we seem to be in agreement there. All right. So part A solved. Part B, what are we going to do? Literally the exact same thing. The same damn thing. So I have complex numbers. I have a rectangular form representation on top, polar form representation on bottom. Both of them are technically true because they are the same thing just expressed in different ways. I express them in different ways so that we can use those parts later on as we need them. All right, so this guy right here is going to be 1.4 kilowatt divided by 0.75 with an angle of the inverse cosine of 0.75. And in rectangular, I got 1.4 plus J 1.235. There's our 9 o'clock projector failure. Might need to talk to eight, 6, 7 with an angle of 41.410 degrees. All right, let me disconnect. I'm sorry, what was that? It has only happened to me in this room, in this quarter, and I teach a class in this room every quarter since this building opened. Correct. Um, yeah, I don't think it's haunted. I think that tech doesn't pay its contractors enough, but I shouldn't have recorded that. Mm. All right, I'm tempted to tell you guys stories, but we need to do things. After this, I will tell you about my lab space that used to be in literally an old hospital on the south side of campus. Yeah. Yeah. Let's see here. So we have complex power absorbed by load one using the exact same thing that we did. Okay. So here's where things potentially get difficult. We need to find the complex power of load two, and we were provided no information whatsoever about it. So how do you think we're going to do that? Yeah, that just literally doesn't have to be any harder than that. So we know what the composite load is doing. And so if we subtract from that what load number one is doing, then the rest has to be what load number two is doing. Absolutely right. So using the values that I had stored in my calculator, I get 1.2 plus J 0.58. Which is 1.333 with an angle of 25.801. All right. And now we're at part D, where we're calculating our capacitor value. And so this is now effectively the exact same thing that we had been doing prior to this problem, okay? So just as a reminder, C is equal to P old tangent theta old minus tangent theta new divided by omega times the voltage drop across our capacitor squared. So what's P old? 2.6 kilowatts. Absolutely right. What's theta old? 34.915 degrees. Running out of room on this page, so I'll just do it here. Theta new is going to be the inverse cosine of 0.98. What's up? Omega is what? Two pi times 60, so 125. And then absolutely right, our voltage across our capacitor is 120 volts RMS. Putting all that together, what do we get? Or if you want to, yeah, not a problem. So let's see, so 2.6. Actually, let me do that as 2,600. The inverse cosine of the 0.98 target power factor that was given in the problem statement. Nope. I said nope only because you said kilo. Uh, I got 331.783 micro. Ooh. That is, so for what it's worth, that seems to be wrong. And I say that seems to be wrong, because the answer that I have given on the page is actually 237.049 micro, which sounds very close to what you just got. Yeah. Yeah. So let's, yeah, 237, I just probably typed something in incorrectly. Uh, Alrighty. So that, to me, I thought was the hardest problem. Scroll back down. .98 was from the problem statement where we were told find C if